Good afternoon, dear colleagues. My name is Olga Zalutska, and I'm pleased to present you the work Probing Textile Composition Cues in Vision Foundation Models through Sample-Level Explainability Analysis on behalf of Marina Molchanova, Olga Zalutska, Alexander Mazurets, Maxim Shurypa, Ilya Timofeyev, and Oksana Zakharkevich. Fiber composition is a key textile property because it affects performance, care, recyclability, and value. Standard identification methods such as near-infrared and hyperspectral spectroscopy are accurate but require specialized equipment, which limits their use for fast, low-cost screening. Instead of reporting accuracy alone, the study uses explainability as evidence. It examines whether frozen models encode linearly decodable composition information, whether attribution maps change with blend complexity, and whether model explanations are more sensitive to texture, color, or contrast-related perturbations. The study uses the fabric composition dataset deposited on Hugging Face and Zenodo. Although the full image manifest contains over 12,000 photograph rows, this work tests the data as a controlled sample-level probing study rather than a large-scale training benchmark. This avoids statistical bias from articles with many near-duplicate images. The metadata subset includes 44 distinct fabric samples. Three derived levels are used: dominant fiber, composition type, and normalized composition entropy. The subset is imbalanced. It contains 5 pure fabrics, 37 binary blends, and 2 ternary blends. By dominant fiber, it includes 19 polyamide, 16 polyester, 7 acrylic, and 2 cotton samples. Here you can see the research workflow of the sample-level probing protocol. The experimental design follows as a sample-level workflow to avoid leakage from multiple photographs of the same textile. The dataset is reduced to complete fabric sample units, and all image-level results are aggregated by sample before statistical training. Zero-shot fiber naming is tested for SILI IP and SIG LIP by ranking 13 fiber names across several prompt templates. Linear probes are there fitted to frozen embeddings to estimate fiber percentages and dominant fiber, with results interpreted descriptively because the effective sample size is small. Robustness is accessed through cross-model explanation stability and counterfactual perturbations of texture, color, and specular or contrast appearance. Statistical testing is performed at the sample level using of the test with false discovery rate correlations, Spearman correlations, and bootstrap confidence intervals. Here you can see the zero-shot recognition and linear probing. And this slide contains two tables. The first one, zero-shot dominant fiber accuracy average over 4 prompt templates and 43 samples with a single best SILI IP prompt shown separately. And the second one contains descriptive sample level linear probing of composition, reporting per fiber regression, dominant fiber prediction, and dominant fiber silhouette in feature space over 43 samples. Also here you can see principal component projections of frozen visual representations for the 4 evaluated backbones colored by dominant fiber. Explanation, structure, and cross-model stability. The attribution maps were spatially diffuse rather than sharply localized. And also here you can see the representative fabric images on the left and the corresponding SILI IP input gradient attribution maps on the right. Attention follows weave, print, edges, and contrast silhouette and contrast structure rather than compact fiber-specific regions. If the models attended to composition as such, more complex blend would be expected to yield more dispersed or structurally different explanations, but they did not. The Spearman correlation between normalized composition entropy and each explanation descriptor was negligible and not significant. And here you can see sample-level mean explanation descriptors by backbone over 43 samples each, and composition entropy against explanation descriptors, namely heat map entropy, attention dispersion index, and top 10% coverage. The regression lines are effectively flat, indicated no association. And and about counterfactual sensitivity and composition effects. So here you can see the heat map shift by perturbation family and composition type. Texture perturbations dominate the relocation of attention for every composition type. This analysis showed that model explanation depend mainly on texture. Texture perturbations causes the largest heat map shift, far above specular and contrast changes and color changes at general. Heavy blur and low pass filtering move attribution maps the most, with grayscale, while grayscale conversion had almost no effect. The result shows that the vision foundation models contain only weak composition-related information. Linear probes perform slightly above the majority class baseline, but negative silhouette scores the mixed PCA projections shows that model representations are not organized by fiber identity. Zero-shot prompting is even weaker. Explainability results clarify this limitation. Attribution maps are diffuse, stable across the models, and mainly focused on the texture, weave, print, and contrast, rather than the composition-specific evidence. Thus, the models do not directly know textile composition. They encode visible surface cues that are only weakly related to it. Two findings are especially important. First, high cross-model explanation stability shows that texture-driven attention appears across architectures, but it does not prove equivalent semantic faithfulness. Second, composition entropy is not linked to explanation descriptors, while composition type shows only a weak exploratory relation through fractal dimensions. In practice, general image features are not enough to reliable image-only composition screening. More robust systems should include additional signals such as near-inflated or multispectral inputs, or use targeted fine-tuning with fiber discriminative supervision. That's all. Thank you for your attention.